Mr. Chairman, shall we start? Dr. Azwani?
Assalamualaikum. Assalamualaikum and good afternoon, everyone.
Waalaikumsalam.
Prof, are you hearing me?
Yeah.
Okay, Prof. Alhamdulillah. All right. So thank you very much to everyone. So we will start our session, our first session with reciting kitab Al-Fatihah. All right. So thank you very much. Thank you very much for joining us in the KPPIM International Webinar 2023 on Mathematical Sciences. Your presence is definitely our happiness. Thank you. Thank you for your support. My name is Nur Hazwani Aguila and I am the moderator for the first session. For your information, the KPPIM International Webinar 2023
second. Just my screen.
Yeah, can see.
Yeah. Um, trying to find my. Can everyone see my slide?
Yes, Dr.
Okay. So again, I would like to thank the Secretariat and organizer, for giving me the opportunity to be involved in this great event, yeah, and also the opportunity for having me as the first speaker for the first section of this international webinar on mathematical sciences for 2023. Okay, um, for this afternoon, I'm going to share with you about the study titled Mixed Integer Programming, MIGP, Model for Urban Battery Electric Buses, Transit Routes Network Design Problem, in short, UEB-TRNDP. So as has been introduced by Dr. Haswani, my area is Information Research or Management Mathematics. Yeah, I hope that you will enjoy this talk. So I'll start with the first uh, sharing with you some introduction and then a bit of literature review, methodology, result and discussion, and the conclusion. So let me start with the introduction. So I think everyone knows that public transport bus network, is an important public transport, So it is basically defined as an integrated set of bus services which allows people to travel from one area to another. And we know that there are a lot of benefits and advantages of public transit. Nowadays, we can see that it is actually to improve uh, the mobility, of people or goods, and also for improving road congestion, instead of driving personal cars or private cars, public transit can be seen as a solution, to reducing road congestion. Other benefits include reduced air pollutions, improved fuel efficiency, and also uh, improving commuters' productivity, as well as equitable transportation system. Transportation is the bloodline of urban life. Yeah? Nowadays, instead of just the conventional bus, we have the electric buses, which aims to reduce carbon emission and the dependency on fossil fuel. And with that, it is very important to ensure that we have a well-designed transit bus route network. This is to make sure that the demand are well served, or in other words, maximization of demand served or number of passengers being served by the transit buses, and also to optimize costs and profits for the bus operators. As mentioned, the study will involve formulation of the mixed integer programming model for solving the urban electric buses transit route network design problem. To ensure that public transit is going to be everyone's preferred choice, the authorities or the uh, public authorities or local authorities should think of how to make this public transit effective and efficient. Yeah? So passengers will expect high quality public transit which are reliable, frequent, fast, accessible, affordable, all sorts of things that is actually for greater satisfaction. So in order to enhance the public transit as alternative choices to private cars, the urban transit network system must be in place. So, the transit network design problem actually focuses on determining a set of transit bus routes which optimizes passenger and operator related objective functions subject to identified operational constraints. So nowadays we can see that we are moving towards public transit electrification. Why electrification? This is due to the concerns over the environmental and health consequences, so that people are looking for alternative fuels and also sustainable or green transportation. That is where the electric vehicles are being the options for this sustainable transportation. So for electric vehicles, we have pure electric vehicles, hybrid electric vehicles, fuel cell electric vehicle, and so on. So with battery electric vehicle, it means that we have the pure electric vehicles powered by battery. And electric buses have now been introduced in Malaysia. The reason being, Malaysia is actually facing the carbon emission or GHG emissions, yeah, where we have been, yeah, dealing with transportation sector being the second largest contributor to carbon emission, yeah, and this carbon emission comes from the road transport. So to meet the Malaysia's commitment under Paris Agreement for mitigating GHG emissions, including carbon dioxide emission, so the government targeted to launch 2,000 electric buses. That was being actually stated in 2014. So the electric buses was first launched in 3 states in Malaysia, Putrajaya, Melaka and Sarawak. And nowadays, we can see electric buses being tried or implemented in some big cities of Malaysia. So we can see that the deployment of the battery electric buses actually, even though new, yeah, it is critical for sustainable transportation. So that is why we can see that many cities are actually embarking on testing or assessing the viability of these electric buses to replace the diesel buses. However, there are issues or challenges, yeah, when adopting these battery electrical buses, yeah, for the transit system. Yeah. Some of the challenges being the range and battery performance, and also issues concerning the charging infrastructure and also battery capacity. So in the BAB-TRNDP, yeah, or Transit Network Design Problem, mathematical programming models have been used, yeah, even before electric buses. So, however, yeah, for battery electric buses, TRNDP, the modeling of this route network or solving the BAB-TRNDP using mathematical programming model are still lacking. Furthermore, even choosing the right parameters or input data for the model are also challenging. So in our study, we are trying to look at different combination of objective functions to be included in the mathematical programming. So in this case also, we can see the opportunities of, we can actually propose some strategies in BAB-TRNDP which could benefit the passengers and also the bus operators. So the objectives of the study first is to analyze the current system and identify the parameters and requirements for this electric bus route network. Second is to formulate the mixed integer programming model for UEB-TRNDP with the objective functions to minimize the sum of vehicle usage, empty travel and charging costs, and also to minimize the total in-vehicle time for the travelers. And the third one is to propose some strategies for this electric bus transit route. Limitation that we have been facing is in terms of acquiring real data for testing the model. So for this particular one, we are using benchmark instances from past studies. So basically the novelty is the formulation of the MIGP model with the new combination of objective function and also modified constraints. And this study definitely significance to various parties, including the society, industry, the government, academia, and also in terms of environment. Let me share with you some literature review. So we can see that urban planning especially will be concerned about this planning and designing a bus transit network. So when designing the bus transit network, there are five main steps or activities involved: designing the routes, setting the frequency, setting the timetable for the bus transit or rail transit, and then fleet assignment, crew assignment, and scheduling. So basically, TRNDP or transit network design problem will deal only with the first and the second one. Okay, so why is it important to determine the set of routes? Because the set of routes will reflect the route length. So that definitely is associated to fuel cost, travel distance, travel time. So in this case, we can see that interest are growing in terms of studies concerning the electric transit buses, especially when cities across the globe are searching for transportation solutions which include electrification of the public transit. So again, deployment of the battery electrical bus system is important to sustainable environment. And I mentioned also there are issues in terms of optimizing charging infrastructure and also battery capacity, which is the focus of the model that is proposed. And what we can see here is that basically the problem has been formulated as mathematical programming model, which include, for example, by Abdul Wahid et al. They propose a mixed integer linear programming model with two objective functions for minimizing charging events based on uniform time slots and also minimize charging event based on non-uniform time slots. For Pilarino et al., they actually formulated mixed integer nonlinear programming model, which objective function is to minimize the implementation cost. And Long et al. Formulated MILP model that is actually aimed to maximize travel reliability while controlling the total cost. Zhang et al. Proposed a mixed integer nonlinear programming to minimize weighted sum of total unsatisfied demand, total percentage travel time, and also total cost. Liu et al. Proposed an MILP model for more efficient operations while concerning about reducing environmental effect. And Jiang et al. Proposed MILP model to determine the number of charging paths and lines operation that minimizes social welfare and propose MILP model to minimize the total implementation cost. So this is basically the analysis on the MILP models of these studies, yeah, which I have mentioned in terms of the types of MP models, the objective functions. But here also you can see the solution methods, as we know that mathematical programming model can be solved using exact or approximate methods. So we have here heuristics and meta-heuristics as part of the approximate methods. As for this study, we use the optimization solver MATLAB to produce the solution. And in terms of data varies in terms of using real network data, real-time data, benchmark instances, or synthetic or simulated data. And these are the data that have been used. There are 3 case studies involved for testing the model, which the first one is small case study, which is just on 8 nodes, yeah. But it is worth noted that um, even for small number of nodes, it's not actually easy to come up with the solution. Yeah. Okay, so we have the medium case, which is 10 nodes, and also large case, 12 nodes. So the second and third case are coming from benchmark instances by Jaramillo, Alvarez. So these are among the preliminary works to be done, which are to prepare information concerning the link or the edges of this network. Yeah, so here we define or we identify the links involved and name it as A. Here for the 8 nodes instances, there are 28 types of links. And from there, we identify the outgoing and incoming nodes for 8 nodes here. For this is for the 8 nodes instances. Yeah. And this is for the second and third case studies, which is based on the 50-node network of Jaramillo Alvarez, which have been adapted to Malaysian Transit Bus Network by Amiruddin 2019, which in this case, Amiruddin actually solved the TRNDP, but not for electric buses. Okay, and these are data for 10 nodes along with the link for OD, yeah, and also the outgoing incoming nodes. And the third case study for 12 nodes, we have the demand data and the link data and also outgoing and incoming nodes. So basically, the research activities involved with the preliminary activities, establishment of data, analysis of data set, and then followed by the phase 2, synchronizing and also adapting, modification, and so on for the formulation of the mixed integer programming model. And the third phase comprised of the computational experiments, and finally the analysis and also establishment of the strategies. So for the formulation, we use 2 base models. The first one is by Jiang et al. 2022, and also the additional objective function for the model is taken from Yanozikova et al. 2012. Okay, and then due to this combination, there are activities in terms of introducing new notations, variables, and so on, synchronizing between the 2 models. Okay, and in order for solving this particular model, we use MATLAB inline proc solver. So the basic requirements, we must have these matrices, the objective function coefficient, the technology matrix, the right-hand side vector, the coefficient of equality constraint, the right-hand side vector for the equality matrix, and also the lower bound and upper bound of. So The research objective 1, which is to analyze the current system and to identify the parameters and requirements for designing the urban electric bus transit. Why is it important? Because we have to make sure that we have the input data and also the right parameters for the model. So there are various studies that have been looked at where we can look at parameters such as the battery capacity, maximum charging power, battery type, and also some other information that are important that might need to be included in the model. So based on these parameters from past studies, there are 7 that we look at. So we have looked or we have actually identified some parameters that or can be adopted for the MIGP model for our UEB-TRNDP. So in this case, you can see some of these. For example, the battery capacity in terms of kilowatt hour, energy consumption, upper bound and lower bound of the state of charge for the battery, charging cost, battery type, yeah, and some other characteristics of buses. For example, the bus length, yeah, the speed, the weight, and so on, yeah, and also the type of electric buses that are normally used or widely being used worldwide. Okay, this is the one that is quite popular. Yeah, you can see these. Yeah, it has speedos and also 12-meter length with 2.55, height 3.05, can fit up to 120 packs. Yeah, there's a longer version which is 18 meters, and the battery type is lithium titanium oxide. Okay, or we have the capacity of 210 kilowatt hours. Okay, so the second research objective is to formulate the mixed integer programming model for battery electric buses transit network design problem with these 2 objective functions. As I mentioned, this is the model formulation after we actually adapted, and synchronized some variables, constraints, yeah, from 2 studies, 2 past studies. Okay, so these are the sets, parameters, indices, info variables, and also decision variables being used. And these are the 2 objective functions. As we are using or treating this as goal programming, so we have the goal 1 being the objective function 1, and goal 2 being the second objective function. Okay, and there are various constraints here which are described here. So we have the equation 1 and equation 2 for the first and second objective function, and we have the constraint 3 to actually ensure each trip is performed once. Constraint 4 is flow conservation constraint. 5 and 6 stage that each vehicle begins and ends its operation at depot. And also there are some other input data or variables that are involved here. And also constraint 7 to ensure vehicle battery energy consistency. And 8 require the upper battery state of charge level cannot be exceeded after recharging. And also constraint 9 to keep the vehicle battery state of charge within safety range. And 10 and 11 to ensure travel demand to be satisfied. And the last few constraints are to actually dictate the values of the decision variables. So for research objective 3, it is to solve the model, yeah, and to establish the strategies for this electric bus transit network. Okay, so this is the summary of results based on the first objective function, which is to sum up, yeah, the total cost for vehicle usage and empty travels with the charging cost. So the total cost include these 2 components, and the solution obtained using the UEB-TRNDP model, yeah, using the first objective or the goal 1. Here, these are the 3 cases. Case 1, there are 2 depot, depot 1, depot 2. Case 2, depot 1, depot 2. Case 3, depot 1, depot 2. And with this information, we have the total charges here being 157, for example, for depot 1, case 1, 198.50 for depot 1, depot 2, case 1, and so on. Okay. All right. So what we have here, yeah, based on the solution, which gives us this total cost for the objective function 1, we can see the road, yeah, that are produced by the model for depot 1, depot 2 of case 1, depot 1, depot 2 for case 2, and depot 1, depot 2 for case 3. So we know that the first case is containing 8 nodes, second 10 nodes, and the last 12 nodes. Okay, and the respective costs. Based on that also, we are able to get the information in terms of the travelers which are using these particular services, yeah, for the road using depot 1 for case 1, depot 2 of case 1, depot 1 of case 2, depot 2 of case 2, and so on. In other words, for 2 depot for each of the 3 case studies. Okay? And based on that, before we can proceed with the second objective function of goal, because this model contains multi-objective, or in this case, bi-objective, 2 objective functions, we have been using the preemptive goal programming method. Yeah, if you have no idea about this, you can also look at textbook by Hamdi Taha. What does it mean by preemptive goal programming? So basically, one of the approaches in preemptive goal programming is where you prioritize the objective function. So in this case, the first objective function is being treated with high priority, so that is why it is being executed first. Okay, but before we can execute for the second objective function, this result from the first objective function need to be added as additional constraint to the model. So, for example, if for depot 1 case 1, we have the minimum value, or the optimal solution is 157. So what you have to do is just add this constraint. If in minimization, we have to make sure it's less than or equal. So this is to make sure that we are not getting a worse solution. Yeah. So we must make sure that we get better, or the current solution is good enough. Yeah. We don't want any less quality solution or degraded of the solution that has been obtained. Okay. So once the additional constraint has been added, so we proceed by executing the model for the second objective function or second goal. So this is the results, summary of results for all 3 cases, case 1, case 2, case 3. And you can see the results here. The total in-vehicle time for all travelers, obtained. This is in minutes, so transform this into hours. We also have the total number of travelers, so that reduce this to, for example, case 1, we have the average time for a traveler, is like 42 minutes for the whole journey, or 44 minutes for the second depot, and so on. Okay, then we can see also that result varies because one thing is that these 3 cases have different number of nodes. For sure they will vary because of the number of nodes, so the journey will be different. And we can see that, for example, the cost for the objective function 1, from the first case to the second case, 43% increase, and for the second and third, not much different, 10 to 12 from the same set of data. So they are not much different, but there is still increase. But for the second objective functions, this is totally varied because of it based on or depends on the travel time that we have, for the network, and also the number of travelers, the number of travelers. All right. So in other words, how many passengers actually board the buses and so on. Yeah. So these are the results for the in terms of routes, obtained using the model. So there are two different colors to represent the result from depot 1 and depot 2 of case 1, depot 1 and depot 2 for case 2, and also depot 1 and 2 for case. So as the conclusion, we can see that well, the battery electric buses, in terms of implementations, they are still new. Yeah? There are so much that needs to be improved. There are so much that needs to be explored. Yeah. So that's actually being the motivation of this particular study. But actually, this study is serving as preliminary work for our grant actually. So this has actually given us some insights of what are the important things to be included in the model for this particular problem. Yeah. Okay. So as mentioned, we have solved this using the preemptive goal programming method using MATLAB, and we have identified that in this case, subject to various constraints such as the cost for charging and so on here that we got actually based on certain assumptions in terms of the parameters. Yeah, for example, the types of battery, the location for the charging and so on. Yeah, because we have two types of charging infrastructure. One is overnight charging, and the other one is on-road charging, which is where these buses have or being charged at the terminal or certain stations or stops. Okay, all right. So with these findings, we hope that it gives us further informations on how we can actually improve in terms of uh, the charging infrastructure and also the battery issues, especially in order to make sure that we optimize. For example, if the buses carry heavy batteries, then it will affect in terms of number of passengers and also in terms of fuel, in terms of the efficiency of the energy. Yeah. So at the same time, bus operators can also minimize vehicle usages, empty travels, and charging costs. Through this electrification. Yeah. Okay. So for future studies, it is recommended that real data being used, hopefully that actually can lead to more accurate results that reflect the actual operations. Currently, we just enclose incorporated constraints that actually being spelled out in some past studies. Yeah, but of course, if we have the actual data, there might be some other constraints that can be included. Yeah, and also using larger number of nodes. Yeah, because what we have been testing is just a small number of depot and also number of stops. Yeah, we have 8, 10, and 12 only. Okay, I'm not saying that it's easy to just deal with it 8, 10, and 12. Yeah, so the in this study, we have been using the inline Prof, but of course, for any mathematical programming model, as I mentioned, you can also employ the approximate methods, heuristics and meta heuristics. Yeah, you can try even the hybrid, meta heuristics. Okay, and but it is to be noted that the meta heuristics produce near optimal solution, as compared to exact method that produce the optimal solution. Okay? So with the current advancements of technology of battery electric buses implementation, future studies can look at some other characteristics, parameter requirements, and also specification to be part of the constraint of the model. Okay, that is all. Thank you so much for your attention. And I would like to welcome if any questions. Yeah, there is any question from you.
All right. So thank you, Dr. Adibah, for your sharing. So now, please, we need a question from the audience. Feel free to type your question in the chat box, or you can unmute, and just ask the question.
May I ask a question, please?
Yes, Prof. You can
Right.
ask, Prof.
In fact, Doctor, your research focus on electric bus, right?
Yeah, for this one, yes. Previously, we also studied on the one on conventional buses.
What is the essential difference in modeling with electric bus and ordinary bus, and except for the charging stations and just neglect them, do we have any difference
Okay.
in modeling, in optimization?
All right. So basically, the concept is the same. Yeah. So the concern in terms of optimization is on the demand served, yeah, and also the operating costs and so on. So but as mentioned, yeah, the most difficult challenges are to make sure that we don't have situation like the buses suddenly out of this power or battery, yeah, because of insufficient charging and so on. So these are the important parts, yeah. So that is why, as I mentioned, the battery capacity, yeah, and also the charging infrastructure are the key differences between the ordinary transit road network design problem and also the electric buses. Yeah, because the 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 concern for the electric buses are over the where do we charge, how many times we charge, are you using the overnight charging or the en route charging, yeah, and also where are the locations of these charging infrastructure, and also if it is battery electric buses, it is important to make sure what kind of battery, yeah, what is the power and the capacity of the battery, how long does it last, and so on. So those are actually the constraints that are imposed in the model. So you are right, actually. The major differences are actually dealing with the charging infrastructure and also the battery issues. Yeah, the battery capacities, type of batteries, the dimension of size of batteries.
So that means you are just adding some parameters, taking that into account, right?
That's right. Yes. So imposing more parameters, more constraints, yeah, and of course there will be some cost incurred, yeah, if we talk about infrastructure and layout.
Okay, thank you. So another question is, in fact, that optimization problem depends on location where you are, then people behavior, then some brand of buses to be used, or even weather condition, or the
Yes, sir.
quality of road and so on so on. Do you have any parameter to take into account all this
Yeah,
in the optimization problem?
those are interesting actually, because why some issues concerning temperature. Yeah, when we use buses, yeah, or electric buses in general, yeah, temperature is one particular issues. For example, too cold also affect the performance of the buses, and too hot, like in Malaysia, for example, can also actually affect the performance of the batteries and also the electric buses in general. So those are additionals on top of these uh, charging locations, yeah, frequencies of charging and so on.
Thank you.
Yeah, thank you also for the question.
Dr. Adibah, I have a question.
Okay.
Dr. Adibah, for your research, for today, your research here, you apply for electric buses, right? So what happens if we apply to electric train? For example, we have electric train in Japan. So what do you think the obstacle that you will face if we 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 do a research instead of electric buses, we have here electric train.
Okay, so actually the research here is on the transit road network design problem. So transit can be any public transport. So for land transport, we have buses and rails. That is trains. Yeah. So this particular problem, the first thing that we must know is the line planning problem. Line planning problem is the routes. Yeah, for example, for trains, rails, transit, we have the lines. Yeah, so if you look at the network of rail, you can see many lines, isn't it? So that's the line. Yeah, so for road transport like buses, we call it roads. Yeah, for the roads network. Yeah, so in terms of similarities, yes, they are similar in terms of the process. You are designing the routes or the line, yeah. But at the same time, when we talk about implementing electric vehicles, yeah, electric vehicles. So again, the concerns is over, yeah, where are the charging infrastructures, how many times that you need to charge. Yes, so battery electric buses of course different in terms of the requirements, parameters and characteristics as compared to train or rail transit. Yeah, but it is applicable. The same modeling process, yeah, same method are being used, except that the constraints and the objective function are being formulated differently because the requirements, the characteristics are different. I hope that I answer your question.
Answer, Dr. Adibah. One more thing is, um, uh, how actually for the objective function you add the parameters, right? You add the parameters. So
For the objective function.
you get the idea actually, the idea to formulate the objective function.
Okay. So in modeling, if you want to come up with the model from scratch, it would be very challenging. Yeah. So what we can do is you look at certain past studies model as base model, yeah, or reference model. So basically, you are not actually taking the whole chunk of the model, yeah. So what you do is you adopt and adapt, yeah. So because why? We want to suit the requirements that are the objectives that we have. Okay, so for example, for this one, we look at two models, yeah, by Jiang and also by Yanuskova. So what we can see here is that we look at the objective functions, yeah. So one we would like to look at in terms of the cost. Yeah, the cost. The other one is passengers don't want to stay in the vehicles or in the bus too long. So that is a preference for customer satisfaction. So we are minimizing the in vehicle travel time. Okay, but if you have other interests, other objective function, for example, yeah, previously if we are not dealing with electric buses, we would like to reduce carbon emission, for example. So those kind of objective. But for electric buses, we normally look at the objective functions such as reliability of the services, and also we look at the total cost of the infrastructures needed. Yeah, and also, for example, in my study, it is on the charging cost. Yeah, for the battery charging. Yeah, and also to look at the customer satisfaction in terms of how long do they have to stay in the bus. But of course, again, when solving this, it depends on the assumption as well. For example, the speed of the bus can make the difference. If you're taking the lower speed, the minimum speed, for example, electric bus, we can have the minimum speed 15 kilometers per hour. That is very long. But if you take the extreme side of the fastest one, which is 70 or 80 kilometers, of course it will be a faster journey or short time journey. But that might not be realistic in the KL situation or urban areas where we know that there are a lot of traffic jam. So that makes a difference in terms of assumption that you make, yeah, to start with. In other words, the constraints of the model. Yeah.
All right, Dr. Adibah, thank you very much for your explanation
Alright.
and sharing knowledge.
Okay. Thank you, everyone.
All right, Prof. Aloy, are you ready now, Prof. Aloy?
Yes, I am ready.
All right, Prof. Now we continue the session with our second speaker, Prof. Aloy from Uzbekistan. Please welcome Prof. Aloy. Here, let me read a short biography of Aloy here.
Rakhmatillo Aloev.
All right. So Prof. Rakhmatillo Aloy was from Bukhara, Uzbekistan. He received his bachelor degree and master degree in mathematics from Tashkent State University, Tashkent, Uzbekistan. His degree in mathematics and physics on computational mathematics field from Institute of Mathematics of the Siberian branch of the USSR Academy of Sciences, Russia, 1985. His doctoral science degree in mathematics and physics on computational mathematics field from Novosibirsk State University, Russia, 1994. Currently, he is the professor of applied mathematics and intelligent technologies, Faculty of the National University of Uzbekistan and UZ, Tashkent, Uzbekistan. He is the main author of more than 120 publications with around 232 citations. Under his leadership, 2 doctors of physical and mathematical sciences, 6 PhD, more than 30 masters were trained. His research interests are computational mathematics, partial differential equation, mathematical physics, information system, and information security. His research interests are computational mathematics, differential equation, and mathematical physics and information system and information security. So without further ado, please welcome Prof. Aloy, who will give a 30-minute talk and 10 minutes for a Q&A session. So please welcome Prof. Aloy. So we have to give a big applause to our second speaker. So Prof. Aloy, you may start now.
Okay. Assalamualaikum. Good afternoon, everyone. First of all, I would like to thank the organizers for inviting me to give a report. Thank you very much. My report is investigation of the exponential stability of an Upwind difference splitting scheme with control parameters for hyperbolic systems. A two-dimensional symmetric T hyperbolic system with constant coefficients is considered. Control parameters are entered. The values of the coefficient depend on the control parameters. A mixed problem or a symmetric T hyperbolic system with constant coefficients is considered. To determine the numerical solution to the mixed problem, an Upwind difference scheme of splitting in directions is proposed, which depends on the characteristic velocities. The question of the exponential stability of the proposed difference scheme and the energy norm is investigated. In my report, we assume that a symmetric hyperbolic system with constant coefficient can be in n plus 1 stages. These stages are controlled by control parameters. Upwind difference schemes are constructed for each of the stages, depending on the value of characteristic velocities. The exponential stability of the proposed difference schemes is proved. Now, we consider the following symmetric systems. You can see in one. Here, V is an unknown vector functions to be determined. A is equal to A transformed, B also, are the given symmetric square matrix of dimension Nn with constant real elements. A special form of writing a symmetric system. Now we introduce into consideration the parameters, two parameters, D1 and D2. D1 depends on the eigenvalues of matrix A, and D2 depends on eigenvalues of matrix B, where lambda q of A and lambda q of B are the eigenvalues of the matrix A and B respectively. In this case, system 1 will take the following record form, form 2. Here you can see R and B. In this portion of this matrix A and B enter the sum of two sign definite matrices respectively, A plus, B plus into non-negative definite part, and A minus and B minus into the non-positive definite part. That gives us the opportunity to construct an Upwind difference scheme for the numerical solution of mixed problems posed for the original symmetric T hyperbolic system 1. Note that the following inequalities hold for the eigenvalues of symmetric matrices A plus I, B plus I. The first of them means non-negative of eigenvalues and non-positive of n eigenvalues. And I want to go to the statement of initial and boundary conditions. As a domain where a mixed problem is stated for the system 1, we consider the domain Q. Q is the set of points t, x, y, where t changes from 0 to to plus infinity, and x from 0 to big X, and y also change it from 0 to big I. It is well known that for the system of equations 1, it is necessary to set the initial condition at the time moment t is equal to 0. Also boundary conditions on x is equal to 0, big X, and y is equal to 0 is equal to big Y. Assume that there exists a unitary matrix P that simultaneously reduces the matrices A, B to the diagonal form. Then system of equations 2 takes the form 3. Here lambda A plus, lambda A minus, and so on are the diagonal matrices. We already know the number of specified boundary conditions on different boundaries of the considered area. As the initial data, we consider the condition 4. Here, phi xy is equal to this one, and phi I xy are given functions. Auxiliary lengths of problem 1. Here we consider two problems. One of them, we consider the following linear hyperbolic equations. Equation 5. Look at here. The coefficient r is positive. Our task is to analyze the exponential stability of these equations with linear boundary conditions in canonical form for x equal to 0. This one, boundary conditions 6, and with initial conditions 7. The mixed problem 5, 6, 7 we will call problem 1. We assume that the functions in initial conditions here U0x from space L2 satisfy for the following consistency conditions 8. And I go to the definition of 1. It is the definition of exponential stability. Equation 5 with boundary condition 6 is exponentially stable in L2 norm if there exist nu and c positive such that for any initial conditions U0 from space L2, L2 is the solution of the mixed problem 5, 6, 7 and satisfies the following inequality 9. You can see in inequality 9 that the norm of the solution little or equal than c exponent minus nu t and the norm of initial functions. Also, you can see here that when t tends to infinity, right side this inequality tends to 0. Let us introduce the concept of a weak solution. You know that there are solution and also a weak solution to mixed problem 5, 6, 7, 8 in space L2. To do this, we multiply 5 on the left hand side by function c from space C1, where t is a given positive number. Then we obtain the following equations. Such equation. Both sides of this identity are integrable over domain 0t and 0L. We assume that solutions U belong to class C1 with respect to t and x. Using the formulas for integration by parts and initial conditions 10, we have equality 10. Let us use the following transformations of the first integral term of the right-hand side of equation 10. First, using initial condition 7, we obtain 1, this equality. Likewise, using boundary conditions 8, we obtain the equality 2. Now, we choose function psi in such a way that the integrand of the integral equation 2 is 0. Then, after transformations of 1, and we obtain the following identity from 10. This equality 12. You see here we used the initial conditions. Instead of U0, you can see here U0x. The key point here is that although this last equation was derived under the assumption that functions u belong to class C1, with respect to t and x, it makes sense even if functions u are not differentiable and can therefore be considered as weak solution to the system. Then L2 solutions are defined as functions u that satisfy 12 for all psi that satisfy 11 when initial functions u0 belongs to L2. The definition of an L2 solution is as follows. Now I want to go to the definition of weak solution. What it means? Weak solutions. Let phi from a space L2 function. The mapping Q is an L2 solution to the mixed problems, our problems 1, 5, 6, 7, 8, if for any t and for any function psi from C1 space satisfying conditions 11, the following functions u from space C not 0 satisfy 12. Now, we consider the following functions is as a Lyapunov form. You can see in certain formulas, it is Lyapunov functions for our problem. In this formula, you can see parameter mu a and exponenta and our functions u square, where this exponenta is equal to exponenta minus nu x divided a. Mu is positive parameters. And now I would like to go to some actual lemmas of problem 2. Now we consider the problem 2. Consider the following linear hyperbolic equations. 14. You can see here the coefficient minus a. It means that the coefficient negative. In problem 1, we have positive coefficient. Now we see negative coefficient. It is problem 2. Our task is to analyze the exponential stability of these equations with linear boundary conditions 50 in canonical form for x is equal to L. You can see here that the boundary conditions is in a right side of our domain and with initial conditions 16. The mixed problem 14, 15 and 16 we call problem 2. Assume that the functions in initial conditions 16 U0x from space L2 satisfied also the consistency condition 17. The definition 1 of exponential stability for problem 2 remains unchanged. Let's introduce the concept of weak solution to the mixed problem 14, 15 and 17 in L2. To do this, we multiply 14 in the left hand side by psi from space C1, where t is a given positive number. Then we obtain the following equation. Psi. Both parts of this identity are integrable over domain. This domain 0t, 0l. We assume that solution U belong to class C1 with respect to t and x. Using the formulas for integration by parts and initial conditions 7, we obtain this equality 18. Here we used integration by parts. Let us use the following transformation of the first integral term of the right hand side of equation 18. First, using initial conditions 60, we obtain 1 equality. Likewise, with boundary condition 70, we obtain the equality 2 also. Here we used boundary conditions, and in the equality 1 we used initial conditions. Now we choose functions psi in such a way that the integrand of the integral equation 2 is 0. For this, it is enough to assume that psi is equal to 0. Then, after transformations of 1 and 2, we obtain the following identity from 10. This identity 20. The key point here is that although this last equation was derived under the assumption that functions u belongs to are not differentiable and can therefore be considered as weak solutions to the system. Then L2 solutions are defined as functions u that satisfy 20 for all psi that satisfy 19 when initial functions u0 belongs to L2. The definitions of L2 solution is as follows. Let phi from space L2. The mapping U from this domain to R1 is an L2 solution to the mixed problem 14, 15 and 17 if for any t and for any function psi from C1 satisfying conditions 19, the following functions u belongs to space C0 satisfied 20. Now For the problem 2, we consider the following functions as Lyapunov functions. The functions 21 is called Lyapunov functions for problem 2. Here mu A is coefficient, mu parameter, Ex exponenta, and our functions Utx. And now we go to construct difference scheme for numerical solution of the problem 1. In domain J, this domain, we construct a difference screen with steps delta t in direction t and delta x in direction x. The nodal points of the difference screen, meaning the intersection of straight lines, t is equal to k delta t and x is equal to j delta x, are denoted by tk xj. The set of the nodal points of difference grid is denoted by gh, where gh is equal to this set of nodal points. And the values of numerical solution at the nodal points are denoted by this one, ukj. Steps of the difference grid gh are selected in such a way that equations, this one and this one, are fulfilled. To find a numerical solution to the mixed problem 5, 6, 7, 8, our difference grid gh, we propose the following difference scheme. Such scheme. You can see here ujk minus uj minus 1k. Initial conditions 7 are approximated as follows, and boundary condition 6 are approximated as 25. As this is difference scheme 23, 24 and 25 is called difference scheme for the numerical solution of the mixed problem 5, 6, 7, 8. Well, let's assume that the steps of the difference grid satisfy the current Friedrich-Levy Kefel conditions. Such conditions, delta t, delta x, this is coefficient a little or equal 1. Now we study the question of the exponential stability of the numerical solution to the difference problem 23, this one 23, 24, 25. First, we define the exponential stability of the numerical solution to the difference problem. Definition 4. The solution to the difference scheme 23 that satisfy boundary conditions 25 is called exponentially stable if there exists positive constant eta and c such that for any initial given data u0 from L2, the solution to the initial boundary value problem 23, 25 satisfies the following inequality. In this inequality, you can see at the left this inequality, the norm of the u, and at the right, the norm of the initial conditions. And here, c and exponenta minus eta tk. Let us introduce the following notation. This one exponenta and coefficient. To prove the exponential stability of the initial boundary difference problem 23 and 25, we propose the following functions as a candidate for the discrete Lyapunov functions 30, such one, 26. To find a numerical solution to the mixed problem 14, 17, we use these different schemes. You see here uj plus 1k minus ujk, when the coefficient a negative. Initial conditions you can see here and boundary conditions. And different scheme 27, 28, 29 is called, we used for the numerical solution for the mixed problem 14 and 17. Also here, we assume that the steps of difference grid satisfied current Friedrichs-Levy, such conditions. And now we go to the to study the problem of the exponential stability of numerical solution to the difference problem 27, 28, and 29. At first, about definition, the solution of the different scheme satisfying boundary conditions 29 is called exponentially stable if there exists positive constant eta nc such that for any initial given data u0 from L2, the solution to the initial boundary difference problem 27, 28, 29 satisfy the following inequality. Let us introduce here also the notation exponential and mu plus. To prove the exponential stability of the initial boundary difference problem, we propose the following functions as a candidate for the discrete Lyapunov functions. 13 is a discrete Lyapunov functions. And about implicit Upwind difference scheme for problem 1. For problem 1, we propose the difference scheme 31, 32, 33. You can see here index k plus 1, k plus 1. It means that we consider implicit Upwind difference scheme. We start with the exponential stability problems of the numerical solution to the difference problem 31, 32, 33. And now we go to the definition 6, the solution to the initial boundary value problem 31, 33 is called Lyapunov stable if there exists positive constant alpha, where change from 0 to 1 and c positive such that for any initial given data u0 from L2, the solution of the initial boundary difference problem 31, 33 satisfy the following inequality. You can see here alpha k, where alpha changed from 0 to 1. We study the Lyapunov stability of the initial boundary difference problem 31, 33 based on the approach of constructing a discrete quadratic Lyapunov functions. We propose the following functions as a candidate for a discrete quadratic Lyapunov functions way. 34 formulas is a discrete quadratic Lyapunov functions for problem 1. And about implicit Upwind difference scheme for problem 2. 35, 36, 37 is implicit Upwind difference scheme for problem 2. And we here you can see here the definition of Lyapunov stability and Lyapunov functions. And now we go to the two-dimensional problem. Here you can see our domain OH and the scheme, the different schemes. You can see in 40 here index L, here L minus 1. It depends on the matrix B. And here L plus 1 and L. And also P for A and A plus and A minus. Now consider the issue of constructing and studying an Upwind difference scheme for the cases CA from 1 to n plus 1 and CB. Obviously, the number of such combinations is n plus 1 and n plus 1. Thus, we propose to build an Upwind difference scheme depending on the sign of characteristic velocities. And we proved such theorem. Let the steps of the difference grid delta t delta y satisfy the current Friedrich-Levy key-field conditions. This one, maximum lambda p delta t delta y is little or equal 1, and difference boundary conditions are dissipative. Then there exists constant c, positive constant, and constant alpha from 0 to 1 such that the solution of the initial boundary difference problem is Lyapunov stable in norm, such norm. Well, let us introduce the following notations for all states. And now I want to go to the computational experiments. For the computational experiment, the following system of Sandvenon equations was chosen. Here you can see the systems and the matrix A, B, and the right side F. Matrix A and B can be represented as such a way. A is equal to A plus plus A minus, and B is equal to B plus plus B minus. And here you can see 25 states, solutions depending on the decomposition of the matrix A and B. And we, after numerical solution, received such results. Numerical experiment for the first variant. Length x 100 meters, width 6 meters, and time and steps, and the parameter u, v, c. And in these graphics, u is the speed in the x direction, v is the speed in direction y, and h is the water depth. And the next experiment for the 7th options. Also, A and B is the speed, C, H is the water depth. For the 13th variant, for the 19th variant, for the 25th variant. In conclusion, a two-dimensional symmetric T-hyperbolic system with constant coefficient is considered. Control parameters are entered. It is assumed that asymmetric hyperbolic system with constant coefficient can be n plus status. These states are controlled by control parameters. Note that the values of the coefficient depends on these control parameters. And we received the following scientific result. Problems of formulation of a mixed problem, problems with initial and boundary conditions for symmetric hyperbolic system depending on control parameters were investigated. And the second result, we determined the numerical solution of the mixed problem. An Upwind difference scheme of splitting in directions was proposed for each value of control parameters. The scheme depends on the characteristic velocities. The issue of Lyapunov stability of the proposed difference scheme in function space was investigated. The Lyapunov stability of the proposed difference scheme was proved. Here you can see references. I finished my report. Any question, please?
Thank you, Prof. Alon. So, is there any question from the audience? You can ask now.
Hello.
Do we have time to ask questions?
Yes, Prof. We have time.
All right. The first question is on diagonalability. Diagonalability of that matrix, because you have somewhere you have such a diagonalability condition. I think that you split the A and the B into two matrices, which are symmetric matrices. So that is a point to diagonalability. Am I right or not? Can you see that? Diagonalization.
Yes, thank you very much for your questions. You are right. We here in our work, we consider only symmetric matrices A and B. You can see from algebra that with the help of one transformation, you can diagonalize two symmetric matrices. One of them is positive. And here we use such information.
Thank you. So another question is regarding that your psi function. You multiply your equation by psi, which is a continuous function. But somewhere you stated that function must be 0. So that means some cases you multiply by 0. It's not good, right? Because you multiply from left-hand side. Psi function. Continue. Are they here? You see? You multiply by psi function, which is continuous.
See, okay, from functions from space C1.
Yeah, this is continuous functions, right?
As minimum continuous functions.
At least continuous function. Yeah, you multiply, but somewhere you stated that psi is 0. So that means you multiply by 0.
Or only in one point. Yeah, means only when x is equal to L in one point. It is boundary conditions. It called boundary conditions.
Another question is regarding your CFL condition. Why you are referring to that condition? So that means without that condition, you cannot solve, or any?
Yes, because it is called a necessary condition for stability.
If no that condition, that non-stable, right?
Yes, it was proved. It was proved in other researchers.
So one more question on your notation, because once you go to numerical solution,
Yes.
then because in your L2, in your case, is integrable by squares functions, right?
Yes.
L2, they are integrable by squares.
Yes, by squares. Big L, it means analytical functions, and a little l means is discrete functions.
That means that are sequences.
Yes.
The ordinary L2.
Not ordinary L2.
Because sequences. Summable sequences, right?
Not sequences. It is a set of functions.
No, I mean small l.
Small l, yes, a set of.
Yeah, because you're passing to numerical solutions. Your functions become discrete. So that's why instead of functions, you would consider sequences. So that's why big L is integrable by their squares, but little l means summable by their squares, sequences.
Yes, you are right. After construction numerical solution, we construct the sequences of numerical solutions, which tends to analytical functions from space big L2.
All right, thank you.
Thank you very much for your questions. Any question, please?
What is a symmetric hyperbolic system?
Symmetric hyperbolic system. You can see here, you can see in one the system of partial differential equations. Such system is called hyperbolic systems if A and B are symmetric matrices. Thank you for your questions.
Thank you.
Please, any questions?
Hello, I have a question. At first, I would like to thank the professor for a well-prepared report, and my questions about in the report talk about the stability of the solution. And my question is, what is the Lyapunov stability?
Okay. Thank you for your questions. Lyapunov stability and exponential stability are equivalent. The definition of exponential stability is equation. You can see 5, it means this one, this equation, with boundary conditions, this one. 6 is exponential stable or Lyapunov stable in L2 norm if there exist the parameters nu positive and C positive such that for any initial conditions U0 from L2 is the solution of the mixed problem, and satisfied this inequality 9. In this inequality, you can see at the left inequality, you can see the norm of the solution in space L2. And at the right inequality, you can see the norm of the initial functions. And the coefficient C and exponenta minus nu t. When t tends to infinity, the coefficient tends to 0. So such definition is equivalent Lyapunov stability. Understand? You understand? Do you understand?
Yes, thank you very much.
Not at all. Any question, please?
All right, Prof. Aloev, I think we should end our session. So before we end our session, so I would like to ask cooperation from the audience to turn on the camera so that we can have a photo session. Would you please turn on your camera?
Thank you very much.
Thank you, Prof. Aloev. Okay, Dr. Rini, you now can take the photo. One, two, three. One, two, three. Okay, Dr. Rini? Okay, so this is the end of our first session. We hope that the participant, the audience, get something from the speaker, of course. And please feel free to contact both speakers via their email. Okay. Via the email, I think I have to share the attendance link. Okay, the attendance link. The attendance link for our session, the first session here, you can scan here the attendance link. Okay, on your, I would say on your right, we have here the KPPIM research domain. Since this the two speakers are from mathematics field, so as a organizer, we would like to promote to promote our expertise in mathematics. So please feel free to visit this page. So from this page, the KPPIM research domain in mathematics, you can find our expertise in mathematics. So we have actually 3 domains. We have 3 domains. You can scan the QR code. You please do a visit here. So we'll get the information. So we can, maybe you can email to them, and in future maybe you can do a collaboration. Okay. So I think, okay, please fill in the attendance form. For UITM staff, of course, you will get the training hours, and for non-UITM staff, you will get the certificate. Okay, as a participant, I will email to you. Okay. Thank you for your support. Your presence is our happiness, of course. See you at the next session, which will be take place on 24 March 2023. With our tagline is this webinar boost our visibility. So thank you very much. Thank you very much. We are really appreciate for your presence. So thank you. So we have to end here.
Thank you very much.
Thank you.
All right,
Thank you very much, everyone.
Bye-bye.
Oldu.